Ladies and gentlemen, welcome to video number 13 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed in late 2017 at the Bibliothèque Nationale de France in Paris. We are today now November 18 in the year 2018, about a year later. Today in this video lecture we shall concentrate on the latitudinal evidence of icosahedral symmetry in the solar ball. Second part of this investigation of the latitudinal evidence, the sunspot zone in the low latitudes. In the contents of part 2 of the book, The Fivefold Sun, we are in section 8, low latitude evidence for or against the presence of icosahedral geometry in the solar ball. The contents of this video number 13, we shall see what are the accepted notions relevant to this region in solar physics literature, and ask what are the main issues relevant to this region, and then we shall see the results found in the book The Fivefold Sun. The accepted notions, they center around the notion of a butterfly diagram, which was first proposed in the 19th century, in which is seen over a solar cycle how the latitude positions of the sunspots develop over time. Their emergence covers a latitudinal span of 30 degrees from the equator up to 30-degree latitude, as is accepted in the field. This was known as 1618, which was the first observed solar minimum epoch and is in Shiner's book of 1630. However, 400 years later, there is no known cause for why the emergence of sunspots is restricted to this latitudinal span. Another accepted notion is that at sunspot maximum epoch, the typical latitude for sunspot may be around 15 degrees, plus or minus 1 or 2 degrees. But there, at this maximum epoch, there is a maximal latitudinal span, i.e. sunspots are seen almost from the equator up to 30 degrees. There is no accepted value for the latitude at which is found the highest density in sunspots, the largest number of sunspots for a given latitude. Note that it is not necessarily the typical latitude for sunspots at sunspot maximum, which corresponds to this highest density latitude. As for the characteristic latitude for the emergence of the first sunspots, the ballpark first estimated by Shiner in 1630 of 30 degrees was refined over time to values of 28 degrees, which is often cited, or also 25 degrees, which is as often cited as found here from an investigation, a meta-analysis of solar physics literature in the last few decades. The difference between the highest latitude for sunspots in general and the characteristic latitude for the emergence of the first sunspots should not be much, because it is absolutely certain that the latitude of sunspots is a function of time from sunspot minimum epoch to the next minimum epoch. So what are the issues that remain to be addressed in as far as this low latitude region, the sunspot zone, is concerned? They revolve around the notion of finding what are the statistically characteristic latitudes for the secular behavior in sunspot formation. What is the highest latitude for the emergence of full-fledged sunspots? We shall try to find an answer to this question for the solar cycle's first rotation. And secondly, what is the actual latitude with the largest number of sunspots? The characteristic latitude for the emergence of new cycle sunspots, which we seek in the first rotation of a quasi-decadal Schwabe cycle, is found in the Fivefold Sun to be 26.3 plus or minus 0.5 degrees. This is in line with the so far accepted values or most cited values of 28 degrees and 25 degrees, and is a sheer refinement of this range. Over several cycles, for a 6-month average or for an 8-month average, depending on how authors define the quantity, the latitude of the first sunspots starting from sunspot minimum epoch has averaged out at 25.7 degrees. In another section, we looked at an exponential fit in Hathaway 2015, where a latitude of 28 degrees is found a few months before cycle minimum and 25 degrees a few months after cycle minimum. In yet another section from data in Ternullo 2007, we found that in cycle number 20, for a time average of less than 1 month after sunspot minimum, the mean latitude was about 26.8 degrees. And in conclusion, we found in the Fivefold Sun that in the first rotation, the characteristic latitude for new cycle sunspots is statistically about 26.3 plus or minus 0.5 degrees. If we now compare this estimate, 26.3, with the suggested icosahedral model for the solar ball geometry, as proposed in the earlier videos of this series of video lectures, we find in the 2D projection of the suggested three-dimensional model made of 12 balls surrounding a cavity, that the center of any toroidal ball in this arrangement is at a latitude of 26.56 degrees, which is defined by trigonometry in this geometric arrangement. This is the latitude of the center radially projected at the surface of the circumscribing sphere, which in the case of the Sun would be the photosphere. So we have here approximate correspondence, coincidence between the latitude at which characteristically the first sunspots emerge in a solar cycle and the vertex of the icosahedron on which this center is superposed. This is a vertex, toroidal vertex of the icosahedron. If we now look at the issue of where is the at which latitude do we have the largest density for sunspots? It is found to try to be very precise with 4 significant digits at a latitude of 10.95 degrees, plus or minus again 0.5 degrees. This is for a 1-month average. It is about the same as a 1 rotation average in the earlier estimate. And this is verified from 1875, maybe even from 1853 to present. First of all, let us note that in the mid-19th century there was a relatively significant database of latitudinal sunspot positions collected by Carrington and augmented by Spörer and other astronomers, in which many authors found a latitudinal density peak for sunspots at 11 degrees. This is the case of Young, the American astronomer and solar researcher. In his 1881 book, The Sun, Young wrote that the peak for the density of sunspot is at 11-degree latitude. Secchi, in 1875, in his book on the Sun, cited from the same body of data an estimate of 10 degrees. So why was this forgotten? We have to wait for 2012 for a Korean author, Heon-Young Chung. You see, his name also includes Young, like the US astronomer of 1881, but this is a Korean scientist who had the idea of trying to best fit the latitudinal distribution of the centers of gravity of sunspot groups in latitude. And he found that the best fit was with a double Gaussian instead of a simple Gaussian, i.e. with a bimodal distribution, the main mode of which by far he found around 11 degrees. And he stated this result from inspection of its graphs and figures. It is here estimated that with 4 digits on his plots, the peak is at 10.95 degrees. In conclusion, this is about 11 degrees plus or minus a few tenths of a degree. This is the secular, statistically characteristic latitude for the density peak for sunspots, and it has been verified for much more than 100 years, so is a robust statistic. It is surprising that for more than 100 years scientists were not much concerned with this quantity. Secchi was the leading astronomer of his time. His book was the main, Le Soleil in French, was the main textbook on the sun in Europe. And Young, who had several editions of his textbook, The Sun, published after 1881, explicitly found this result, but it was forgotten. There is actually a secondary latitudinal density peak, which is a much lower peak, much less density at 20.5 degrees, according to the analysis in Heon-Young Chung, for again a 1-month average. Heon-Young Chung worked on the Greenwich data. and based on a much smaller body of sunspot positions in the late 19th century, Young again found a similar result, and he stated in his textbook on the Sun that the two peaks in density are at the latitudes of 11 degrees and 22 degrees. So again, we have here a solid statistical basis to determine the precise location of this secondary peak. We can now have a look at our icosahedral arrangement to see how it may help us understand this low latitude phenomenology of the sunspot zone. Here is shown a 3D model over which we have a red dot showing a latitude of approximately 30 degrees, poleward of which, as we reported, there are no sunspots. We see in a ribbon ring a latitude of about 10, 11, 12 degrees, where we reported that the largest density of sunspots is found. Why is it so low in latitude? Why is it, in fact, at this very specific latitude and not at any other place in the latitudinal range from the equator to the pole of the Sun? If we now open this 3D model, we have a surprise inside. Inside is a wire model of the suggested icosahedron inside the Sun, which was already shown in an earlier video to illustrate the several remarkable angles in such an icosahedron. Now it is shown in a hemisphere of a spheroid like the Sun. Is reminiscent of what Kepler did in 1596, but the circumscribing sphere in the model reported by engravers of Kepler's contraption, this sphere represented the solar system, and an icosahedron was embedded in it, but inside other polyhedra, regular polyhedra, and was hardly to be glimpsed as a very small figure inside this Keplerian arrangement. Now this kind of construction is shown here as suggested to be representative of the interior of the Sun. And on the wire model is superposed now a white sheet of paper which represents a front face and a second face next to it. The tip of one of the two faces is in the northern hemisphere, and the tip of the other face is in the opposite hemisphere. Is shown on the center of the face having its tip in the southern hemisphere, the center of this face at 10.812 degrees, as is found from trigonometry. So you see 10.812 degrees is the latitude span from the equator of this model to the center of the face of the icosahedron, which is in this model. I remind that at each of the vertices we have to imagine a ball about this size that is centered at the vertex here and at each of these vertices. The vertices here in this planar ring we call in the Fivefold Sun the toroidal vertices of this interior icosahedron, imaginary icosahedron, and the faces that are between these vertices and the equator we call the toroidal faces. So we have a rough coincidence of the latitude at which are found the most sunspots with the center of the face of the icosahedron. 10.95 degrees as found to be statistically significant in observations of the sunspots of the sun, and here 10.81 for the precise value of the center of the face of the concentric icosahedron. Now, what about the secondary peak in the density of sunspots, which is found to be at 20.5 degrees since Young in 1881 and confirmed rigorously by the analysis by Chang in 2012. Well, if you subtract from the latitude of the center of the toroidal face the value of half the icosahedral central fivefold angle, which is 31.7 degrees, you find 20.9 degrees. But this will be because of the subtraction in the opposite hemisphere. So we show here as another dot, red dot, the latitude of this point, which corresponds to, in this face, having its tip in the northern hemisphere, the center of the face being here at 10.8 degree in the southern hemisphere, which you cannot see. And the corresponding point to be obtained from this center face is here in the southern hemisphere at 20.9 degrees latitude away from the equator. So we have again a correspondence with some imagination of the secondary peak with an icosahedral angle in our suggested arrangement. It remains to be seen why there would be a secondary peak that would be constrained or defined by the subtraction of half an icosahedral angle. We can now turn to, in conclusion, icosahedral interpretation of secular latitudinal behavior in sunspot formation. Sunspots are found to emerge in the toroidal faces of the concentric icosahedron in the suggested configuration. First, the first new cycle sunspots appear at the latitude of the top vertex of toroidal faces. The latitude of the peak density for sunspots coincides with the latitude of the center of these toroidal faces, 10.8 degrees. And the latitude of the secondary mode in sunspot density is offset by half a central icosahedral angle and is at 20.9 degrees in the opposite hemisphere. Can we say that in the toroidal faces of the suggested concentric icosahedron is to be found the toroidal magnetic field of the Sun? This would be a parallel with what was suggested for the polar caps, in which we found that inside the suggested polar ball in our arrangement is contained the poloidal field of the Sun, as was discussed in videos 11 and 12. If we now have a look again back to the set of icosahedral angles that had to be checked in this project to verify the presence or not of such fivefold symmetry in the solar ball, we can see that we have now Here the angle of 10.8, which is now found. This angle is now found, and this angle was found for the latitude of the first sunspots. So we have now a full set of icosahedral angles checked, which is consistent with the presumption of the relevance of fivefold symmetry to the actual constitution of the solar ball. This is now, ladies and gentlemen, the end of video 13. In the next set of videos, we will investigate the longitudinal phenomenology of the solar ball. I thank you for your attention.